So after 6 units of electricity and magnetism, this is the moment we've been building up to, the creation of electromagnetic waves. There are 3 ways to create electromagnetic waves. One way, as you see listed here, is by accelerating charged particles. I'll talk more about that in just a moment. Another way to do it is particle annihilation. We might talk a little bit about this later this term. But basically you have matter, you have some matter particle that collides with its antimatter partner. So the common example is an electron that has a collision with an anti-electron. The anti-electron is known as the positron. It's the exact same as the electron, except its polarity is positive. Its charge polarity is positive instead of negative. And if they collide, they annihilate each other and EM waves are emitted. The other way is for an electron that's orbiting, that's in an orbital for a molecule or an atom. An electron drops to a lower orbital. We will talk about this later this term, but when this happens, an EM wave is generated. We're going to focus, though, on this first one right now, accelerating charged particles. They emit EM waves. And we just need to focus on this idea of acceleration. Remember, there are 3 ways to accelerate, essentially. Speed up, slow down, and of course, change direction. So those are the 3 ways to accelerate. So if you have a charged particle that's doing any one of those 3 things, an EM wave is going to be emitted. So this has some important ramifications that I want to discuss right now. Let's realize that everything that we interact with in our daily lives is made up of protons, electrons, and neutrons. In other words, everything that we interact with is made up of charged particles. Okay. And we know that those charged particles are moving. We know that the individual atoms and molecules are moving because we know that the objects that we interact with have a temperature above 0 Kelvin. Well, most of the things we interact with are, maybe not most, but certainly a lot, are solid. Right? And so for those solid objects, that means the individual atoms and molecules, they don't actually move around, they're just vibrating. Well, if they're vibrating, that means at some point they have to slow down so that they can start vibrating the other direction. They got to slow down and then they're going to speed back up and slow down. It's going to be almost like simple harmonic motion. And so that means they're going to be accelerating. And if those atoms or molecules happen to be charged, guess what? They're going to emit EM waves. Essentially, this statement means that everything, every macroscopic object that we interact with that is above 0 Kelvin, in other words, everything, is going to emit EM waves. That's very important. Now, down here at one of these bullet points, let's see, it's the 4th one, and I know that's small type, I apologize for that, but it says, some examples of EM waves are light, UV, infrared, radio waves, microwaves, not the oven, gamma rays, and X-rays. Okay, so as I was just saying, everything we interact with is going to emit EM waves. And it turns out if you're talking about animals emit heavily in the infrared. If you've seen the movie Predator, any of the movies, the Predator movies, the predator, I've read that he's supposed to see in infrared. And so when they switch to the predator's view, what it's supposed to be looking at is an infrared, and the people in the predator's view are generally represented as being reddish. And that's because humans, just like all animals on this planet, emit heavily in the infrared. And we're actually going to talk more about that later this term. But for now, again, we can realize that, accelerating charged particles emit EM waves. We know that everything that has temperature means that the molecules are moving. And we can also reason through that some of them, those particles, probably most all of them, are accelerating, which means there's going to be EM waves generated. Now, all of these EM waves move the same speed in a vacuum. 3 times 10 to the 8th meters per second. We commonly refer to this as the speed of light. It doesn't matter if we're talking about visible light. It doesn't matter if we're talking about ultraviolet, infrared, radio waves, microwaves, gamma rays, X-rays. It doesn't matter. They're all EM waves. When they're moving through a vacuum, they'll all move at the speed of light. And you may wonder, why do we have all these different names for all these waves? We don't have different names for sound waves, right? They're all just sound waves. We might say, oh, that note is A or something like that, but we don't have different words for sound waves. So why do we have different names for EM waves? That's because historically, when people discovered them, they didn't realize they were all the same phenomenon. So they would discover it and they'd say, oh, I've discovered this thing. I don't know exactly what it is, but I'm going to call it X-rays. Hey, I've discovered this thing. I don't know what it is exactly, but I'm going to call it microwaves, etc. And then people came to realize, oh, these are actually all the same thing, but they already kind of had these names, so those names have just kind of stuck with us. Ultimately, these names generally refer to EM waves that are at a certain frequency range. Sometimes there's some overlap. It's not a big deal. They're just rough guidelines anyway. But that's why they all have different names. One thing I wanted to mention here has to do with these are all waves. And remember that we have our formula for wave speed. V equals the wave speed equals frequency times wavelength. When we're talking about EM waves, we represent the speed of light with the lowercase c. And so we commonly, for EM waves, we just write it like this. C equals frequency times the wavelength. But of course, this is the wave speed. It's just a very specific wave speed, 3 × 10⁸ meters per second.